presentation today comes from Maciej Best from ETH Zurich.
Okay, thanks. So welcome. I'd like to speak about a very recent class of models. You probably all heard about the recent model called DeepSeek R1 or OpenAI's O3. I'll be speaking about these models today and sharing our insights from the research we've been doing in the domain, starting from really giving a very broad perspective of what the reasoning in this domain really is, how it started, sharing some insights in the process, and then finishing with this newest class of models. Very briefly about myself and towards about my own research, I'm broadly interested in sparse irregular computing, where we are dealing with processing of objects such as sparse matrices or graph structures, and it really borders and overlaps with a lot of domains, including things like LLM ecosystems, generative training and inference, different types of databases, parallel graph algorithms, and a plethora of other things. So that's one big part, and the other part is how to run these workloads efficiently on the underlying parallel resources so that these computations are fast, effective, scalable, and simple to manage, to program, and to deal with in general. So as mentioned, we have the so-called ongoing reasoning revolution, that we can call it. So we probably heard about models like DeepSeek R1, OpenAI's O3. And just to give you the very perspective of what's going on there at a very high level, late last year there was a benchmark called Frontier Map, which really was supposed to test the limits of what AI can do with mathematical reasoning. Terence Tao, who is like a superstar in mathematics, you can see the awards of this guy on the right side, field medalist winner, really stated that these are really, really challenging and it will take AI years to catch up with that level of reasoning. And then less than 3 months afterwards, O3 from OpenAI came and solved pretty much more than 1/4 of these tasks. It was like last year, right? So we are even more ahead with this development of these models. So that's very, very powerful class of designs. And now let's take a look at how they actually look like, what can we do with them, how can we make them run more efficiently. But to do it, let's really take a broader look at what is the overall LLM processing pipeline in general. So as we all know, we have some raw data that we are using in the pre-training process to obtain the first version of our model, the general LLM model. Right? Then we apply a couple of different fine-tuning stages that are making this very first rough model better and better in, for example, instruction following, in talking to humans and doing other tasks. And finally, after a couple of stages, so there's a lot of research into how to make these fine-tuning stages more effective. There are tons of different designs, but importantly, at the very end, we have the model that we can interact with by sending the model messages called prompts and receiving the replies that we are going to refer as thoughts. Right, and now we've been seeing a growing development in making this pipeline a part of the bigger compute landscape that we can refer to as the generative AI ecosystem. That consists of two large parts. The top one is the training related, and the bottom one is the inference related. And we've been seeing development into different types of ways of making these models more enabled, more powerful by, for example, plugging in tool usage so that they can use some tools like Python scripts, web browsers, giving them access to, for example, multitude of models, so we can also run these models and talk to them, like to groups of these models and talk to groups of these models, make groups of these models interact and collaborate on solving problems, giving them web access or access to some external data sources, and also involving the so-called prompting structures. That's something we are going to start with today, because that's really the very, very root of what this reasoning of these language models really is, these prompting structures. So historically speaking, it all started with the very simple input-output prompting, where you basically send the model a question and you get the answer. So there's like no really interaction, there's just a single question and a single prompt and then the answer from the model. And we normally provide a question that consists of the section called in-context examples, so we kind of try to guide the model, not by training, but really just providing the examples in the prompt, so there's no training at this point. We just give the sort of template for the model on how to solve the problem we wanted to solve, and then we pose the actual question, and we hope that the answer will be correct. And in that case, we can see that in the very beginning, the simple input-output prompting was, well, we can see the answer was not very correct, and that's what basically made the motivation for trying to involve more structure in this prompting process, in this early reasoning stages. So the big thing there was the chain of thought paradigm, where we are basically, instead of giving the model this kind of plain answer, we are kind of trying to steer the model and to guide the model through a sequence of reasoning steps. We can see these steps underlined with the highlighted with the blue color. That's really what chain of thought is about. It's giving the model kind of a sequence of steps, explicit steps that can be modeled as a chain, and then hoping that the model will get the answer in a more correct way. And actually, as a matter of fact, it does help a lot. So the model is mimicking this chain of thought reasoning in its own answer, giving a sequence of steps, and usually it really helps a lot with the accuracy of the answers. So this chain of thought is a very powerful technique that we all like a lot. But then we had a lot of other developments in the meantime. So there was something called self-consistency of the chain of thought, where basically we, from the single input, from the same input, we are sampling a number of these chains of thoughts. And then, for example, picking the best one. And that also helped even more. So this way we had a bigger chance of eliminating the bad reasoning chains and preserving only the good ones. Then in May 2023, we had the development of the so-called tree of thought, where this process got even more structured, more involved, more graph-like. And the tree of thought enabled us to kind of have this exploration of the next potential reasoning steps at every possible step of the reasoning, right? So there was an explicit tree where at every step of this reasoning process, but again, always remember that still in context learning, so it's still no training going on here. This is just the model giving the next steps as we prompted, and allowing this model, in that case, in the tree of thought case, to give the next stages of reasoning at every possible step. And then the next step that we decided to take was the graphical reasoning, which was really inspired by how we humans think. So as a question to you, when you as a human want to solve a problem, what your thinking process could look like is that you may have some goal to be achieved, you may come up with some idea, then you may be having another idea, then you may want to merge these ideas into an even better idea, maybe then conduct some plan of action based on these ideas, execute some action, conceive the next idea, and repeat this process in a very, very unstructured way until you finally arrive at your goal. Right? And now, if we take a look at this structure on the left, so the question is, does this structure on the left look like these very tree-like structures on the right? Well, not really, right? So we can see really this more arbitrary structure of our more arbitrary graph rather than a tree or a thought or a chain. And that was the motivation to introduce the graph of thought, where we basically enable the LLM user to drive the model, to guide the model through the sequence of steps that can form arbitrary graph structures, complex reasoning patterns, right? And we make it in a principled way, namely we introduce the so-called thought transformations, where a given thought from the LLM can be transformed in one of three different ways. It can be either used as a source to generate a couple of next reasoning steps. That's what tree of thought already does, so that's nothing really new here. But then we also provide the enhance step, where the thought can be refined iteratively in the iterative process, using the loop that we use to model it in a graph structure. And then the aggregate thought transformation, where we can take a couple of different thoughts or even a couple of different reasoning chains and combine them synergistically to produce an even better outcome. That's really the main power behind graph of thoughts. So let's take a look at an example how this could look like in practice. So let's say that we want, so this may be a very funny use case, sorting of numbers, but we took this as the kind of first example because it's a very fundamental problem in computer science. So why not just start with sorting? And to sort a sequence of numbers, you would, for example, split this number into smaller chunks. So you would have like a parallel couple of different reasoning steps, exchanges with the LLM. Then you would sort these smaller chunks by the LLM. So these would correspond and can be modeled by the enhanced thought transformation. And then you aggregate using the aggregation operator in graph of thoughts. And it actually works really well. So it may be again sound funny that we are using LLM for sorting numbers, but for example, tree of thought or chain of thought were not able to do it at all. And graph of thought was really quite effective with the sorting of these sequences. But then, of course, you want to use it for something more realistic. That's what we did as well. So we did use cases such as keyword counting or NDA merging, where in the latter you have like a large set of legal documents like NDAs, and you would like to merge them, maybe, for example, preserving some style or preserving some information, eliminating some other information. That was one of the use cases. And again, the pattern is very similar here, so we can actually, again, apply this principled way of applying the generation thought transformation, followed by the enhance, followed by the aggregation to make this make these tasks work very effectively with this with the LLM using graph of thoughts. Underneath, what we are doing is okay, that's very strange. Sorry. Okay, now it's better. Yeah, thanks, sorry. So underneath we can see the architecture. What is happening is that we have a large module called the controller, which is like the heart of graph of thoughts, and that's the module that the user interacts with to kind of drive this reasoning structure. Again, the prompting, which means in context learning all the time, no training yet. Right, so we have the user talking to the controller. In the controller, there is a part called graph of operations, which is like a template for the reasoning structure. It's a template that can be either provided by the user if you know the structure of the problem very well, or it can also be generated by the LLM itself for certain algorithmic templates. And now the controller talks to the LLM because, of course, we use the LLM as the main kind of driver for the reasoning, and we use it via the parser and the prompter modules so that we kind of have some control over the output from the LLM to parse it appropriately. And we use this output from the LLM to create the dynamic structure called the graph reasoning state, which is like really a graph of these ongoing thoughts coming from the LLM and their dependencies. So we keep the information from the LLM, the actual thought from the LLM, with some metadata that tells us about, for example, how good a given thought is in terms of the solution. We care about some solution, we want to get it from the LLM. So how close are we, according to some ranking, to this solution, for example, right? So that's the information we keep. And we build this iteratively until at some point we decide, or the LLM decides, because we can do it either via the LLM or via some heuristics, if a given solution is good enough to basically be our desired output. So it's very nice, it's very nicely extensible, so we can actually parameterize it to solve your problems, and lots of people have been using it so far, so also you can go ahead and try to use it for your own prompting in context learning challenges. Now some data, I started with sorting, so let's stick to sorting. We can see here on this a little bit complicated plot, so what we are doing here is sorting 32 elements, and the x-axis are different baselines. So we can see this IO prompting, chain of thought, different variants of tree of thought and graph of thoughts. The blue bars on the right y-axis are corresponding to the token cost. So this is what we count in dollars. That's actually how much it costs you to run it via, in that case, OpenAI API. So the lower the better. And the left side is the number of incorrectly sorted elements. So it's accuracy, and it's again the lower the better. And you can see that, as expected, chain of thought and IO prompting are not too great with the accuracy, so they are actually incorrectly sorting lots of these elements, but they are quite cheap, right? And then tree of thought and graph of thought are kind of comparable in terms of costs, but also in terms of accuracy, because graph of thought is kind of only slightly better, right? So why do we care? Well, we care about because as we increase the complexity of the, oh, by the way, we also experimented with different variants. So like for these structures, for example, for tree of thought, what is the number of levels of the reasoning? What is the number of children? But then what really matters is that as we increase the complexity of the problem, so if we go, for example, to 64 or 128 elements, it turns out that the difference between graph of thoughts and these other approaches are really becoming bigger and bigger. So in terms of the costs, we are kind of comparable to tree of thought, or at least some of its variants. Some of them are more expensive, some of them are slightly less expensive. But then the accuracy is really going badly for all the other baselines, including tree of thought. And that's really because they are fundamentally not able to do this aggregation of reasoning paths. So if you actually, as a tree of thought, you would be just searching the search space through the space of potential answers, and you cannot really use the fact that you can split the task into smaller subtasks and then combine them back into a bigger solution. Right? So that's really what we do in graph of thoughts, this synergistic reasoning of combination of different types of thoughts. And the same for the other use cases. So here we can see keyword counting, same pattern as before, basically. So tree of thought is kind of comparable in cost depending on the variant. IO prompting and COT prompting are the cheapest, but again, they all fall short of the accuracy of what we can achieve by this merging of paths. Okay, so we can check all these other details because we have lots of details, including some attempts to explain in the fundamental level why we're having these results. All these things are in the paper. You can check it online. And now let's move on to something more interesting, or maybe not more interesting, but more general. Because we saw I promised you the reasoning language models, so we need to, let's move there step by step, right? So the next step is, okay, we have now all these elements at the bottom. Still all these elements are in the inference domain, and we would like to kind of use them to more, let's call it more versatile reasoning, right? So we would like to not only do some prompting, but we would like to maybe understand better what type of structures are more efficient for what problems, and then do some more, let's say, reasoning in the real world, namely use our scheme to solve some problems, such as, for example, maybe booking some tickets for me or doing something like that. So let's move there again step by step. What we did also early last year was introducing the framework called topologies of reasoning, which is really trying to understand in more detail for different classes of tasks what prompting structure is more effective or cheaper or basically more powerful and more desirable. So for this, we introduced a blueprint for arbitrary structured prompting schemes. And I'm only going to go through very high level here just to give you the idea about the complexities that we are tackling on the way. So for example, we studied a lot of different topology variants because there were introduced in the meantime a lot of different schemes that were trying to use different types of structures for different types of reasoning. So this included things like k-array trees, tree of chains, some schemes were doing something as simple as one-level tree, so it's again something much simpler but also more cost-effective. The question again is, how does it compare to other schemes? There are also binary trees of reasoning, and then different types of graph topologies. So we have, for example, arbitrarily directed graphs, simple graphs such as branch and merge, again something even simpler than arbitrary graph, but potentially more cost-effective. Other types of directed graphs, and even hypergraphs. So there were even hypergraphs of thoughts at this point introduced, and the question was really, what is the principled way of thinking about these schemes, right? So what is the relationship between the structure of these reasoning schemes and their efficiency for different types of tasks? And it goes even deeper because you can think about stuff like what is the scope of the topology? Basically, what is the size of your prompt? Because inside your prompt, your message to the LLM, you can not only include a single thought, but you can actually include the whole structure of thoughts, and then you can combine these structures of thoughts into bigger structures, right, by talking to the LLM. So there are a lot of other kind of corner cases and aspects of building these topologies. I'm going to skip them very quickly because this is actually quite a lot of information, but it's really showing the complexity of these designs that you have to care about when you want to select something or build something from scratch. So we did this for you, and we kind of analyzed all these schemes and built a blueprint, and then analyzed these schemes in this blueprint. Basically, one row in this table is a single scheme, and then it's like which features it supports, et cetera, et cetera. So again, no need to take a look at this in detail. What is important are some insights. So we took all these schemes and these classes of scheme and kind of matched them against different types of tasks like arithmetic reasoning or common sense reasoning or like reasoning with tools or stuff like that. And we arrived at a couple of conclusions, like general conclusions, that for example, chains are in general very effective for simple sequential reasoning. So if you actually have some simple problem, like simple mathematical problem or simple common sense reasoning problem, it's actually best to use chain of thought because it's really cheap and it's quite effective with these kind of simpler tasks. But then if you have something more complicated, especially in the domain of arithmetic or symbolic reasoning, then actually tree of thought is going to be better, much better than chain of thought, and it's highly recommended to use it. And then the point is that the graphs of thoughts are actually almost always more powerful than trees of thoughts, but they are also a bit more complicated to use and to build because you have to kind of reason about this aggregation, understand the structure of your problem better. So if you do have time budget to do it, then it's better to use graph of thoughts because they are not only going to be more effective, but also cheaper. Because again, the other cool thing about graphs of reasoning is that by being able to kind of combine different paths of reasoning, you don't discard, for example, if you have failed reasoning paths, you can still use them for something useful and not just discard them, right? So it's actually a more cost-effective solution than just tree of thoughts, which is just searching through the space of solutions and discarding all the failed paths. But then again, we have these topologies of reasoning, we understand very well what structure is better for the reasoning, but then we would like really to have this reasoning also operate in the real world. So as I mentioned, we have these more complex tasks that involve interacting with the web, with the tools, and stuff like that. And for this, we also have a solution that we recently developed. But before we go for the solution, let's take a look at the actual example tasks here. So for this sort of real-world reasoning tasks, we have a very good benchmark called the Gaia benchmark, released by Meta like a year and a half ago. And just to give you some idea, so it comes with a large number of tasks that are grouped in 3 different levels of difficulties. Level 1 is like the simplest, level 2 is kind of the mid difficulty, and then level 3 is really hardcore tasks. And now we have, let's take a look at an example level 1 question. So it's like the simplest category question, right? You can see that this is some question about the enrollment count of the clinical trial of some sickness for some patients from a certain period as listed on the NIH website, right? And that gives you already some idea about what we are dealing with here, right? So these are tasks where the model has to access some website which is just given by the name, right? So it has to actually look it up first, find it, go to this website. It may be completely arbitrary, right? It has to look for some knowledge there. It might be inside the PDF file, so it has to download this file then. It has to do some reasoning about the data from this file and then maybe combine with some other knowledge. And it's still the simplest level task. Because as we move on into harder tasks, here we can see an example level 2 category task. We can see that there is some photo with some nutrition facts from some whole pint. So there is already some multimodal reasoning involved, some pictures which are completely like not very nice. You have to actually sweat a bit to get some information from that picture. And then the question is again about some reasoning involving maybe some website, maybe some tool execution, maybe some database access, some picture. So again, it's more complicated. And then an example level 3 difficulty task is even more crazy. So it's like question about the presence in space of some astronaut from some photo. That photo is somewhere on some website, and again, some reasoning. So really complicated stuff for the models to solve. And this benchmark is, even though it was released like quite some time ago, it's still posing a lot of challenges for these models. So that's what we decided to target as well with this structured, principled way of reasoning. And this is what we just basically released a couple of days ago. It's called Knowledge Graph of Thoughts. It's tackling these specific tasks with this, again, structured graph reasoning. So here the key idea is really that we propose to use a knowledge graph, which is basically, you can think of knowledge graph as a graph that contains some additional information about the edges and the vertices. Like if your graph models network of people, a knowledge graph would involve fields like name of the person or type of relationship, is the person a father, a mother, whatever. Right? So this is kind of like the enriched graph. And now we propose to use this graph to encode the task statement itself, right? So we would now be taking these tasks that we saw before, and we'd be building the graph from these tasks, from the contents, and then we would be iteratively adding more knowledge to these graphs by interacting with the tool set, making these graphs more and more rich to contain more and more information, and then at some point deciding by the LLM, okay, I have enough information in this knowledge graph, and I will now use this information from this very nice graph format to give you the answer. So that's what we did, and you can see now in an example. So we have some example task, again from level 3, so again the hardest task from the Gaia benchmark. So there is some YouTube video from basically March 2018, narrated by the voice actor of the Lord of the Rings Gollum. And now the question is really, what number was mentioned by the narrator directly after dinosaurs were first shown in this video? So again, some multimodal reasoning. There is a video involved, there is a website involved. There are some questions about basically who is the actor, this voice actor here. So what we would be doing now in our knowledge graph of thoughts is as follows. In the first step, we would be kind of taking the statement itself and transforming this to the graph format. In that case, we can, for example, build a simple graph that contains the Gollum node and the Andy Serkis node, right, with the edge interpreted by. This is like the first bootstrap step. And then we do the next step, which is basically using some tool, right? So this is kind of like the iterative process where we are asking, kind of doing some reasoning to decide if we have enough information or not. But overall, we are kind of iteratively running different tools as selected by a special LLM. In that case, we would be basically querying the web for additional data, and we would be, for example, adding these two edges here, the Silmarillion and We Are Stars. Right? So these are both are kind of films with this actor. And we continue this process with different tools, right? So we have this tool set. In that case, it was like the web search. We can also do, for example, text inspector, because now we actually want to get this information from this video. So we are running some YouTube transcriber, another node that we are inserting. And we repeat this process iteratively till we have enough information as knowledge graph to kind of give the LLM, make the LLM give us the answer. In that case, we solved this task successfully, and the answer is some number that you can get from that graph. Right, so underneath, there is an architecture that basically consists of three big modules. One of them, the central one, is the controller. which is like the coordinator, right? So it kind of manages the whole process, and it consists of two bigger submodules. One of them is managing the LLM interactions with the graph, and the other is managing the interaction with the tools, right? So the graph executor is kind of growing the graph and extracting the information, growing the graph, querying the graph, etc., etc. And the tool executor is, as the name suggests, is interacting with the tool. So it's selecting which tool to run the tool, get the data, parse the data, and pass it to the LLM graph executor. And now the cool thing is that it turned out in this whole process of this research that the results really depend on how we query the graph, because we have a lot of different ways to query the graph. We can query the graph with, for example, writing a script in Python with some general purpose language, with Python or other general purpose language, or we could also use, for example, a dedicated so-called graph query language. It's like SQL equivalent of graph structures. Right? And we actually provide support for both, and it turns out that they are kind of complementary. So there are many tasks where one of them is going to succeed and the other is going to fail, and vice versa. So let's take a look at some numbers. What you can see here is a slightly complicated plot, but let me explain it to you. So the x-axis is our different comparison baselines grouped in groups dedicated to basically zero-shot prompting, right? So here in the zero-shot category, we are just asking the model to give us the answer without any kind of framework that is using the tools or doing something like that. It's just plain model and the task statement, and that's it. Right? Then we have this kind of mid part, KGOT, which is, as the name suggests, our scheme knowledge graph of thoughts. And we have kind of a couple of different variants. So for example, we are using the Neo4j backend, which means that we are using graph query language to query for the answer. Or maybe we are using network X, and then we have kind of different subtypes. So this is not very relevant at this point. These are just different ways to kind of build these queries that we are sending to, for example, a graph database or a graph backend. But, and then we have also this KGOT fusion. So that really refers to a variant of graph of thoughts, of knowledge graph of thoughts, which is kind of combining these advantages. So for example, if there is an execution that uses graph query language, and if there is an execution that uses, for example, the Python, we kind of combine their strengths, and this is kind of the union of these results, right? So, and then the final one is an important comparison baseline. It's basically another framework which is very high in the leaderboard. It's kind of the main Hugging Face leaderboard scheme called Hugging Face agents. And now the cool thing is that we are using this, so here we are comparing to two models, GPT-4o and GPT-4o mini, and we also compare to Hugging Face agents that is using both GPT-4o mini and GPT-4o. And now the left axis, the y-axis on the left is basically number of solved tasks, right? So the higher the better. And now the interesting thing is that we are really outperforming this Hugging Face agents baseline, both. So if we, for example, so all these models here for KGOT are using GPT-4o mini, right? So we are all running the very cheap, the small cheap model, and we can see that we are always outperforming Hugging Face GPT-4o mini equivalent, right? So we are always better for the same fixed type of the model. And of course, the same for the zero shots. But what is even more interesting is that we are able to match or outperform even the variant of the Hugging Face agents that is using a much more powerful model, namely GPT-4o. Right? So that really shows, and we now have a more detailed breakdown of these costs, because these costs are another very important comparison dimension here. So here on this plot, we can see the y-axis is basically the cost of running a given set of benchmarks. And again, we see the zero-shot variants, KGOT variants, and Hugging Face GPT-4o and Hugging Face GPT-4o mini. And we can see that this is like the main advantage of knowledge graph of thoughts. It's not just increasing the accuracy of the outcomes, but it's really enabling cheap models to do these complex tasks for you. Because we are able to basically match the performance on these tasks of a much more expensive and powerful model while having nearly the same or in some cases even better ratio of solved tasks, but reducing the costs by pretty much more than 20x. Right? So this is kind of the main message here, that by using this graph structure inside the prompt, making the knowledge more structured, it enables these cheap models to also get the right answers much more often than with the more powerful models. So, so these two are next steps, right? So the topologies of reasoning and the knowledge graph of thoughts, very recent outcome that we prepared. But now really the question is, because again, we started with DeepSeek, we started with O3, so where is this thing, right? And now this is basically the question. We have all these things at the bottom, and now really the question is, how can we instill this behavior inside the model weights themselves, right? That's really the core of the reasoning language models, basically making this reasoning, this structured reasoning, kind of the part of the model weights and not just having a framework on top of the model, right? And for this, let's take a look. So basically the main enabler here is adding the reinforcement learning stage, right? So that's really the main thing that has been used to make these LLMs able to reason explicitly is adding reinforcement learning. By the way, this is kind of a long talk, and maybe there are some questions about the previous parts. So if there are some questions, maybe you want to ask them now, or are we going to keep to wait? So if anybody has a question about graph of thoughts or anything in between, then go ahead. Mm-hmm.
Okay, fantastic. So I can see a lot of potential in this application whenever you want to have some deep thoughts, say, about the prompts, right?
Deep thoughts, okay, yeah.
Deep thoughts, right?
Yep.
But what about the other problem? That would be whenever you have very long prompts. Because that's a different matter in the sense that your model had to keep track of long-range correlations, say, in the input itself. Does this approach helps in that respect too?
Yes, so they all help you in that, and let me explain how they help you. So, for example, for graph of thoughts, what we did was basically, I mean, these problems that we are dealing with were quite long also. They were involving very long prompts, and in the process, what you can do, and this is also, so this is what we did as basically use cases in graph of thoughts, and then we studied this more extensively with other schemes in topologies of reasoning, was okay, you could now think about taking this long prompt and splitting this into smaller prompts that are kind of having explicit graph structure and smaller structure inside, right? So now you could basically, graph of thoughts is taking these long prompts and you could arbitrarily split them into smaller prompts, and then the edges between these smaller prompts are something that the framework kind of maintains, right? That's our graph of thoughts as well. It's like the explicit graph there. We call this we have like a name for this in this topologies of reasoning paper where we call this type of structure explicit. You have explicit graph, which means you take a potentially very long prompt and you split it into smaller nodes. They contain some smaller chunks of information, but you still have the graph structure, which is kind of having the semantics of why there is a connection between these two prompts, right? And then the framework kind of takes care of solving the problem. So that's one potential kind of example how we approach this. And then the other thing is that these knowledge graph of thought tasks were also quite extensive. So these prompts also contain quite some information, right? And there it's also showing that now this translation process that we take these long prompts with potentially lots of unstructured information, like for example, we parse the whole website. It will contain a lot of data, right? So what we are doing there is taking this and extracting the graph from it, this knowledge graph. And it's again showing that it's going to be both more succinct because this structure is going to contain only the relevant information, and this is going to be like smaller, but also a structure form will make the reasoning more effective. So I mean, I would say that natively these both schemes support this thing. Yep. Okay, so we can probably continue. So as mentioned, we have this very new class of models, right? So this is basically, I'm going to show you that to a large degree that's taking this graph structure of reasoning from the inference part and instilling this graph or at least tree structure or chain structure inside the model weights, right? And we saw these models, so they are, for example, DeepSeek R1, it's QWQ from the Qwen family, or O3 or O1 from OpenAI. And they've been doing a lot of fuzz on the internet, right? So they are really, really powerful. And we also have done quite some study on that, so we started this work pretty much right away after the release of O3, and we have this blueprint that enables us to kind of test different variants of models. So like the purpose of this work was to have a playground for trying different design choices for training a model like that, and having a principled way to arrive at the best design choice, and then training the model from to conduct this reasoning. Right, so let's take a look at what these RLMs actually are as promised. Right, so these RLMs, like examples are O1 or O3 or DeepSeek. So they stand on 3 pillars. So I mean, they have been enabled by 3 pillars of Computer science, the pillar are standard LLMs, right? So standard LLMs are kind of at the core of it in the sense that they come with the huge understanding and knowledge of the real world inside their weights, right? So basically these, like the standard LLMs are one pillar, and they really serve as the kind of database for the reasoning because they contain all this incredible knowledge about the world inside their weights. But they cannot do this reasoning they can do some plain reasoning, some simple reasoning, but they are not very effective at that because, again, it's not very like deliberate, structured reasoning, right? So, but they are still like one of the big pillars. So the second pillar is reinforcement learning, right? So here is basically we're going to delve into more details about what I mean with that. Let's wait like 10 seconds. Almost there. Oh no, it's too early, sorry. Maybe I can... Sorry, Brian. Okay, so we have reinforcement learning. And okay, let's continue, and you guys maybe will try to I will try to communicate this information away. So, so the second pillar is reinforcement learning. That's really the skeleton of reasoning. So this is kind of, as we'll see, RL gives us the way to structure this reasoning in this kind of deliberate, principled way of forming a tree of thoughts, or maybe like a chain of thoughts, or something even more complicated. But again, RL on its own will not get us there, because RL on its own is just a structured way to search for a very large search space, but on its own it doesn't have this information about the real world or anything like that the LLMs on the other hand have. And the third pillar is, of course, HPC, because these models are incredibly expensive to do, as we'll see, and that's why HPC plays here an even more major role than with the plain LLMs. Okay. Yeah, now it seems it's fixed. Thank you, guys. So reinforcement learning, right? So we know LLMs. I've been talking about LLMs for a while now. So let's now move on to the second pillar, to the reinforcement learning. And we are going to see this on an example of using Alpha. We are going to use AlphaGo as an example. So AlphaGo is this very, very established reinforcement learning engine that was famous for basically winning 4 out of 5 matches against the best Go player in the world, Lee Sedol. Right? So what we are doing in RL is pretty much searching through, there are many different ways of doing RL, and kind of one principled way is to use the so-called Monte Carlo tree search. It's like building an explicit tree of solutions and searching through this space of solutions by using this tree, right? So in our case of the Go game, like a single node in this tree is going to model our state of the game. So at some point we have some root, and then we are using a thing called the policy model to basically generate other solutions from the other steps, thus solutions from that root solution, right? So we are now using a neural network called the policy model to basically generate a couple of next steps. And this is going to be very expensive because, for example, in AlphaGo, we could have as many as 1,600 expansions per single move, right? So the tree is very, very, very wide and also quite deep, right? So there's there's quite some compute to be done here. But then we also need another model called the value model to kind of drive the construction of the tree, because we don't want to explore the whole tree because that's clearly infeasible. That's out of the game, right? So that's why we want to only select a subset of this tree, and to select which one is kind of the most promising, we are using another model called the value model. So it's trained in a special way to just give us the insights about, okay, a given solution is kind of the most promising, grab it. And so we kind of continue like this until we arrive at the very bottom of the tree, which is pretty much when the game is solved, when the game is done. So there is a win-win or some other ending outcome of the game. That's where the search ends. Then we are kind of iteratively updating this tree with more and more information and retraining these models, these value and policy models, kind of to refine these reasoning searches. And this is how these models more or less work. These reinforcement learning models more or less work. So now how do we combine this with LLMs? It's actually quite similar. So what we are doing there is also having MCTS search. We can also think about these schemes as based on the MCTS search. But now the contents are usually going to be something more real-world related. Here again, I use the sorting example, but it's going to be quite informative because basically what we are doing, we are again having some input statement of the task. In that case, it's sort these numbers, and we still use the MCTS, and we still use, again, the policy model to generate next steps. So we are kind of building this structure of reasoning explicitly again. And now we can see that these next steps are pretty much some steps of reasoning, and some of them are pretty dumb, like these numbers are blue, or sorting is simple. This is not going too much, it's not very promising part of the tree, but then others are kind of more promising, right? So like look up quicksort, or split this into 2 sets, right? These 2 are kind of much more promising. And we are continuing like this, selecting the best ones, the most promising ones, and continuing. And we are again using this policy in the value model. But here, in that case of the RLMs, these models are actual transformers, and even more, they're actual LLMs. Right? So we have the whole autoregressive process of inference at every step, at every move in this game, right? So that implies that it's actually going to be really, really expensive, because what we are doing, again, remember, there may be thousands of such steps per single step, and the tree may be very deep. And each of these steps is going to involve running the full inference LLM pipeline. So that's really expensive, right? And that's why, by the way, these models are actually not really that large. So, for example, DeepSeek R1 is, in principle, having 600 billion parameters, but this is like a mixture of experts. So, like the active ones are only less than 40 billion, so it's not really that large. So these models are, in principle, not too big. Thus, the name reasoning language models is actually more appropriate than large reasoning models, for example, right? Just for the naming. But anyway, so let's take a look at our blueprint, because now what we provide in our paper is basically the architecture and the blueprint for building different types of these models, experimenting with different design choices, trying different training strategies, etc., etc. So what's happening in this blueprint is that there is the user that is going to interact with the inference module, and then there's, of course, the training part and the self-learning. So the self-learning is kind of the part where we do this reinforcement learning. Right? And now what we do, at the very beginning, we do provide, so usually there's going to be some supervision involved at the very beginning, right? Because we need to start somewhere, and start somewhere means there is some supervised data that we are going to use to bootstrap the value and the policy model, right? So we need to kind of bootstrap these models. That's what pretty much all of these designs are using. And then we are using this training to update, to basically generate data. So this is where we are kind of beginning with our rollouts, with building the MCTS tree. So this data generation is using the reasoning scheme as the central part of the blueprint. And we are building this scheme and running these models and generating more data that we are then using to update the models, right? So we are putting this data in the replay buffer. This is like the name from AlphaGo and AlphaZero. And we are updating these models iteratively with these rollouts. But of course, we also use these models in the inference, because at some point user comes and wants to actually use the models. So we are using these models for the inference as well. And then also inference uses this reasoning scheme. And we also gather the data from this reasoning runs, from this inference runs, and also using them to continually update these models. So that's at a very high level how the blueprint works. You can take it and basically like parameterize it to suit your own needs and your own strategies for training and for inference. In the paper, we provide much more details about how this is actually done underneath, so there is a lot of more going on underneath. We have extensive discussions about that. And also we provide the blueprint understood as a toolbox for you to try now and try different design choices without coding too much, without thinking too much about how to implement these things. We just provide you the blueprint and implementation of these different design choices. And then one example design choice is the granularity of the steps. Because as we saw before, the kind of most, let's say, straightforward way of thinking about the reasoning step itself is that it's like a step in the mathematical proof. Or maybe like we saw here in the sorting example, like one of these steps would be look up quicksort. The other step would be pick pivot, right? So like a very coarse steps. But we could think about also doing much more, let's say, fine-grained steps, and also applying some other ways to compare these steps and to assess these steps. And we also support that. So we support pretty much arbitrary granularity of these steps, such as, for example, single token steps, right? So we could think of also building these reasoning trees or chains where a single node is not like a whole step, a sentence, but really just a single token. Then there are many more of these other design choices that we studied and we also implemented, like the structure itself, so can like just a chain, or maybe a tree, or maybe a graph, or maybe even a nested graph or nested tree. There are also schemes doing that, and we also support that in the blueprint. And lots of other of these choices, like how do we grow these structures? So there are different so-called strategies, like MCTS that I spoke about is one of them, but we also have others like the beam search, or we have even others like ensemble methods. And also the way that we now grow these structures at a very fine level, like the so-called operators, reasoning operators. So for example, we could think about generating, refining, aggregating, pruning, or restructuring these structures, right? So that's what we support in our blueprint. And even more, so I'm going to skip that, but again, there are lots of things you can experiment with and try yourself. And our implementation is called X1. You can try it, it's public, and it provides you with the kind of way to easily experiment with design choices and build your own reasoning models. We do have some initial data because we're also working on our own reasoning model that we are going to, that we call nano RLM, and we have some preliminary data, but it's very, very preliminary. So we have some data for the MAF 500, AMI, and AMC data sets, comparing with zero shot, comparing with a variant of reasoning called self-consistency, this SC, and then this MCTS with either a certain variant of our own current version value model and MCTS with just pure simulations. And we do have some improvements, but I don't want to spend too much time on that. They are very preliminary because we are basically preparing for like really large scale runs to get the actual high quality reasoning model from that blueprint. So by doing this reinforcement learning, we can really take these structures that we know from all these graphs of what schemes, from the reasoning, from the inference part, and really instill it in the weights of these models themselves through applying this iterative reinforcement learning process. Right? Do we have time for, how much time do we have left, by the way? Or? Okay, then I have exactly 10 minutes for the last part. So now I want to kind of steer a bit away from, so okay, maybe there's a question about RLMs, because now we are going to kind of leave the RLM realm a little bit, and maybe there are some questions. Yep, go ahead. I mean, so the costs are, like, I would say that it's very hard to compare it to, let's say, tree of thought or graph of thought, because like tree of thought doesn't involve training, right? It's purely in context learning, right? So I don't really have concrete numbers for, like, okay, so on one hand, like, if you train the model yourself, right, it will not like cost you anything to run tree of thought because you have the model, you host the model locally, right? So like you don't have to pay, but of course there's like the training cost, right? And the training costs are, I mean, for example, one scheme that was showing some reasonable results using MCTS3. So they actually conducted, like there is a work from Microsoft called R-star math. So they kind of trained the MCTS-based RLM, and they had some reasonable results for the different math benchmarks. And I recall that their costs were like 100K GPU hours pretty much. So just to experiment with all these MCTS variants, train the model, etc. Right? So that's, I would say, it's kind of the minimum order of how much you have to throw at the compute to actually get something reasonable out of it. You mean overfitting, that they are really overfit to some specific math? So you are suggesting that we kind of apply this reinforcement learning also in between, like pre-training, or? I mean, that's a good question, right? So I don't really know, to be honest. I mean, if you take a look at how DeepSeek R1 was trained, they do have like a bunch of phases, so they kind of intertwine this reinforcement. I mean, they take the base model, of course, but then they have like reinforcement learning that they apply a bit more of SFT, right? So I would say that's probably a good idea to try, but that would, of course, involve a lot of resources because, I mean, if you really want to do this reinforcement learning somewhere in between pre-training, for example, to maybe instill it better, then it will obviously involve a lot of resources, right? So yeah, we'll see if we have resources for that. And but just to maybe a little bit expand on that, there was also like very interesting work. Because again, there is also like another aspect of this question is, do these models actually memorize or do they do some real reasoning, right, in between? And there was this very interesting work by Anthropic released last week about like the way to understand the internals of these models. And they have like a way to do it by modeling the reasoning as a kind of also, by the way, simplified graph. So they call this tool attribution graph. So they kind of have a way to take these complex models, like with all the weights, and kind of simplifying them in a way that they model these weights as nodes in the graph, sort of. But it's kind of a simplified view, but they still have quite some complexity in this model itself. And then they, for example, like basically track which of these activations were lit where, and they kind of combine these into paths and into graphs. And they basically, like the results imply that they, for example, were throwing these kind of multi-step reasoning tasks at these models, and they were kind of then comparing to like single reasoning tasks, like single-step tasks, and they actually have some insights that this reasoning is actually doing the reasoning. So there's like a two-stage process in the model itself going on, right? So it's like just a side note, basically, about it, that whole process. Okay, so we can probably continue. So on to the very last part, because so it's going to be kind of steering off this whole architectures into a bit more different territory, because now when you think about it, all these forms of reasoning, they all require some sort of verification, right? I mean, the model will give you some answer, maybe the final one, maybe the intermediate step, and you always need to somehow want to verify the correctness of this answer, right? And this is also what we call hallucinations. I mean, they will often hallucinate, and even if you have RLM, it will also hallucinate, right? So that's kind of the big issue here. And now how do we tackle this, right? So we need verification, but for verification, what we really need, to be honest, like the very fundamental thing we need is robust comparison. To get robust verification, we need robust comparison. And I'll explain in a minute why this is the case, but let's start with this robust comparison of outcomes, right? So what we really want to have is some, because again, it's very simple to kind of compare or analyze the outcomes of very, very simple questions. Like if you are asking about some mathematical question, then the answer might be easy to get, and it's kind of easy to compare to answer because the ground truth, because you just can compute it somehow, right? But then if you have these kind of complex problems, like for example, summarize me a text, right? This is like very hard to think about a very robust way of verifying the outcome of such a statement. Like if you want to summarize a text, or maybe a document, or maybe merge to, for example, as a lawyer, you would like to merge two legal documents in some specific way, pay attention to some specific aspects of these documents. And again, how do you verify the outcome, right? It's very hard. So again, for this, we need robust comparison first. And I'm going to give you kind of one example. So on the left, we can see we are basically asking the LLM to generate some story about some things, like and now these two answers are basically telling about two very different things. So these two pieces of text from the LLM are very, very different in what they describe, but they are very similar in how they look like, right? So the syntax is very similar, the structure of the paragraphs is very similar, but the upper one is basically telling about some ancient oak tree and some forest, and the bottom one is about some art gallery. Right? And now the ones on the right side are basically having very similar meaning, so they both speak about very similar part of reality, but they look very differently, right? So they are actually one of them is shorter, the other one has some longer sentences, etc., etc. And now you want to kind of have a robust way of comparing these things in a way that you want the model to be able to tell you that the ones on the left are really different and the ones on the right are really kind of the same meaning, right? And now it turns out that existing approaches like BERT score, so there are lots of things to do it actually. So there's a thing called BERT score, self-check GPT, and they are all failing badly. And the only variant that was like a very recent one, self-check GPT with a certain variant called NLI, it's actually doing this reasonably well, but it's really slow. Just to compare these two variants, like these four pieces of text takes like 360 seconds. So this is pretty infeasible. And for this, what basically we are proposing is something we call check embed. It's really a way to compare these things in a very simple way, at the same time in a very fast way. So let's again recap what others are doing. So other schemes, for example, will take, let's say we have reply 1 and reply 2. And these could be, for example, like reasoning steps or anything that we have in the domain of LLMs or RLMs, or some answers. They both contain two sentences, and each sentence has some number of tokens. And now, I mean, they are kind of similar they are slightly different, but fundamentally they will do all-to-all comparison of all these tokens pairwise in both replies. So BERT score would take plain this sequence of tokens and the bottom sequence of tokens, just compare them all-to-all, and then do something with this matrix of comparison values and kind of get some score from it. Self-check GPT is slightly more involved, but it's fundamentally doing the same thing. What we propose is to pretty much embed these whole sentences, run them through a powerful LLM, just once, embed them into a single embedding, and just compare these single embeddings and get the single score, and the score will tell you how similar these things are. And actually, it's really simple. It's naively simple, but it's actually working quite well. So here what we can see is basically, so we have three plots. I mean, so the data on the left are quite old, so this is like the quite old model. But then we have like also newer models here on the right side. And what all these three plots are showing is basically the x-axis is showing the comparison baseline. So it's like check embed, different variants that we parameterize with different embedding models, and we compare to this BERT score, self-check GPT, and then the y is basically the score, which means that the higher is the more similar a given pair is. Like a single data point in these statistics plots, in these violin plots, single data point is like a number given to two replies, right? So, and these two replies can be either very similar or very different. And now if you take a look, all these other schemes are having this overlap, namely, there will be some replies, pairs of replies that they will kind of mix as, for example, if they are very similar, they will take that they are very different, and vice versa. While for all these variants from the check embed that we propose, there is no overlap or very minor one overlap, which means that it will almost always tell you correctly if two replies are the same, it will tell you they are the same or like similar meaning. If the two replies are very different in meaning, it will tell you correctly they have very different meaning. So that is this robust comparison of different types of replies. And now why do we need this for this verification of the reasoning steps? Well, because there is the established way of trying to see if a given reasoning step or the answer from the LLM is correct or not is to run the question with the LLM a couple of times and see if the LLM is kind of giving you the same answer or if it's giving you different answers. So if there is, for example, like a very binary yes-no question, if you ask this question to the LLM 10 times, if it gives you 10 times yes, there is a very high chance that the answer is actually correctly yes, and the LLM is correct. But let's say you ask the LLM again 10 times this yes-no question, it will maybe, if it tells you, for example, 6 times yes and 4 times no, it means that it's probably not very certain of the answer because it's kind of like giving you both types of this answer, and thus there's a very big chance that the answer is incorrect. And now what do? We now take this check embed idea and we apply this to these very complex problems. And we do it because now what we are doing is basically running this a couple of times, right? So we run the complex question a couple of times via the LLM. And then we take these answers and we run them via check embed. We get the embeddings from these answers and we compare how far are these embeddings in the embedding space. And now if they are close to each other, it means that there is a big chance that the LLM is certain of the answer, and thus there is a high chance that the answer is actually correct. Versus if these embeddings are far away from each other, there's like a large variance in these scores, that implies that the model is probably hallucinating the complex answer, right? So that's what we do. We don't really have much time to, because we have much more data about this, so we have like this data that we show in detail. Okay, we run some question 10 times, we compare it 10 times to all the other questions, and we kind of analyze this correlation matrices, but I don't have time to really speak about it. But again, the idea is that if there is a high variance in these answers, that means that the model is hallucinating, and that means that the answer is probably not correct. And vice versa, if there is a low variance, that means that the model is certain, and thus there is a big chance that the answer is actually correct, and that's exactly what check embed does for these very complex, for these complicated problems. You can check the details in the online draft, and with this slide I'd like to conclude, and we'll be happy to take any other questions. Thank you.